These are a set of nunchucks. Now, what if I told you that these nunchucks, using a specific field of math, can be related to a donut?
The specific field I'm talking about here is topology, which is the study of geometric surfaces under constant deformation.
Let's dive deeper into this concept. Say, for example, we make two Play-Doh objects, one a cup and one a torus, which is just a fancy way of defining a donut-shaped object. Let's look at both of their geometric qualities. A coffee cup has curved sides, a handle, different radii, and varying surface curvature, whereas a torus has uniform circular symmetry, smooth curvature everywhere, and no sharp transitions. Geometrically, these shapes look entirely different. If you measure their curvatures or their distances, the numbers wouldn't match at all. Let's try and look at both of these objects topologically instead. If we were to apply continual deformities to the coffee cup, as we kept going, we would see the cup slowly transition into a torus shape if we manipulated it correctly. This is the heart of topology. No matter how two objects or shapes differ in a geometric perspective, they can quote-unquote become, in a way, the same shape when looked at in a topology lens. If we were to replace the cup with our nunchucks, we can achieve the same thing by simply connecting the two endpoints together. Technically speaking, topology is called rubber band geometry for this exact reason. If we were to stretch a rubber band into two distinct shapes geometrically, they are effectively viewed as the same due to the rubber band's elasticity. So, problem solved. We now know that we can morph our nunchucks into a donut using topology. But in what ways do the two differ? What can a pair of nunchucks do that a torus cannot topologically? Suppose we turn our nunchucks into an object with two endpoints connected by our chain. If we stop to look at it for a second, it kind of seems like a graph, another mathematical structure that connects endpoints to edges. But the key distinction here between our graph and our nunchucks is that there is a flexible chain connecting the two. Since our endpoints aren't static or bound like in graphs, our nunchucks can be viewed as a curve or 1D manifold in topology. What we have just discovered is powerful because we can use our nunchucks to model a fundamental part of topology. These 1D manifolds and curves are crucial to things like configurations, 3D rotation, and symmetry, all of which are repeating and reoccurring in nature. Adding motion into the mix complicates things, but makes our previous findings even more powerful. Suppose we were to move our nunchucks around in a symmetric and repetitive state. Maybe in a figure 8.
Start.
How about a vertical figure 8? The main thing to note with our nunchuck structure is that due to the chain, we're able to achieve a middle ground in which the sticks of the nunchucks are independent of each other, but can only move a relative amount due to the chain. Technically, what we have just unlocked is the world of SO3, which is a rotation group that covers all possible 3D rotations. SO3 has multiple applications. For example, it can be applied to mechatronics, where we may need to rotate multiple parts of a machine due to its structure, or physics simulations involving chains and ropes. Let's look into more topology topics that stem from the presence of our chain. We have already established that the chain is a flexible connector, meaning it does not need to be situated in a straight line. If we were to look at things like proteins in biology, we can see this phenomenon in action. There's a distinct flexibility that the proteins carry within their structure that makes them functional. Another topological scenario arises if I try and loop the chain around my wrist. This effectively creates a braid or a knot around my wrist. A subsection of topology covers this entirely, knot theory. The applications of knot theory are practically limitless in the chemical world. Biology, for example, deals with knot theory with DNA, since DNA can sometimes tangle into knots. Some enzymes have functions that can untie these knots and undo them. Another close and similar field, chemistry, deals with knot theory as well, since knotted molecules do exist, and their stability can be predicted with advanced knot theory. There are even more applications for knot theory, but if we were to go into depth on every single one, this video would be over 40 minutes long. So we've covered practically every use case and property that nunchucks have topologically. Now let's compare both donuts and nunchucks topologically and see what main features they share. Since the two sticks of the nunchucks are connected together by the chain, we can technically say that something can traverse the surface of the nunchucks infinitely or indefinitely. Anything that shares this property is called a closed surface, and toruses are no different. Since they have no free ends, no breaks, and every point on the surface is connected without boundaries, we can say that both the donut and the torus share a closed nature.
I just want to say from the bottom of my heart, thank you for watching. It means a ton to me, and if you could support the channel in any way, either by clicking my links or by leaving a subscribe, leaving a like, etc., it would be greatly appreciated. I'm going to be posting more, so stay tuned for more content like this. Thank you for watching. I'll see you next time. Take care.